Imagine flying from New York to London in under an hour. Sounds like science fiction, right? What if I told you that by the end of the decade, it could be our reality? Today we're diving into the mind-bending engineering breakthroughs that are set to shatter our current understanding of air travel, shrinking distances and making our world feel smaller than ever before. Forget supersonic. We're talking about a future where your commute across continents is faster than your morning coffee. The race to engineer humanity's fastest air travel isn't a dream. It's unfolding in labs, wind tunnels, and test ranges right now. And the innovations emerging from that race are on the verge of redefining global connectivity and transforming how we perceive time in transit. If endless layovers and marathon flights have drained your enthusiasm for global travel, consider this. The biggest barrier between you and the rest of the world may no longer be geography, but technology. Today we're unveiling the revolutionary engineering feats aimed at obliterating those limitations, replacing them with unprecedented speed, efficiency, and possibility. Let's start with the ghost that still haunts every conversation about fast travel, CONCORDE, the legendary aircraft that promised to usher in a new age of supersonic flight, and did, but only briefly. CONCORDE was beautiful, iconic, unimaginably fast for a commercial machine. It cruised at Mach 2.04, cutting transatlantic travel times in half. People forget this sometimes. CONCORDE actually delivered the dream. It worked. So why did it disappear? Economics, engineering limitations, environmental concerns, and regulatory pressures formed the perfect storm. Jet fuel inefficiency, maintenance complexity, the sonic boom issue, and limited seating capacity outran its benefits. And by the early 2000s, the world quietly accepted that supersonic passenger travel had stalled. Since then, commercial aviation has plateaued around the same subsonic speeds we've used since the 1960s. Faster flights stalled for decades, not because we lacked imagination, but because we lacked the materials, the propulsion technologies, and the computational tools to push beyond the limits that grounded CONCORDE. Now that's changing. This time what's coming isn't a slightly improved supersonic jet. It's a technological leap that breaks through the barrier altogether. Mach 5, Mach 7, and beyond. The key difference between now and the CONCORDE era is that engineers are no longer trying to squeeze more efficiency out of 20th century tools. They're inventing entirely new categories of propulsion, new classes of heat-resistant materials, and new aerodynamic solutions specifically designed for hypersonic travel. The next era of fast flight isn't an upgrade, it's a revolution. Let's start with propulsion, because this is the heart of the breakthrough. At subsonic and supersonic speeds, air-breathing jet engines work by compressing incoming air, mixing it with fuel, and igniting it. But these engines hit a hard limit as airflow becomes too fast to manage. Hypersonic speeds, Mach 5 and up, change everything. Three key technologies are defining the future. Ramjets. Ramjets operate efficiently at high speeds because they have no moving compressor blades. They rely entirely on the aircraft's forward momentum to compress air, but even they hit their ceiling around Mach 4. Scramjets, supersonic combustion. Ramjets, or scramjets, are the breakthrough. Instead of slowing incoming air to subsonic speeds, scramjets combust fuel in a supersonic airflow. It sounds simple, but it requires unbelievable precision and engineering finesse. The combustion has to occur in milliseconds. Turbulence, shock waves, fuel mixing, and pressure gradients are all happening at extremes. The scramjet is what makes Mach 510 travel achievable, and prototypes have already proven functionality in controlled tests, both in the US and internationally. But to maintain sustained, hypersonic flight, engineers need more than just propulsion. Pulsed detonation engines. The wild card is pulsed detonation propulsion, a system that uses controlled detonations instead of continuous combustion. These produce shock waves that generate thrust more efficiently than traditional engines. They're not fully matured for hypersonic passenger aircraft, but research suggests they could be integrated with scramjet systems to enable even faster, more efficient flight. Hypersonic propulsion is only half the puzzle. The next challenge is survival. At Mach 5, temperatures on an aircraft's leading edges can exceed 1,000 degrees Celsius. At Mach 7, even more. Conventional aluminum alloys melt, titanium weakens. Even advanced carbon composites struggle at these extremes. Engineers have had to invent new material families to survive. Ultra-high temperature ceramics. Materials like zirconium diboride and hafnium carbide can withstand temperatures far beyond what metals can tolerate. They're being researched for leading edges, nose cones, and engine inlets. Thermal protection systems. Instead of one rigid material, these systems use layered structures that dissipate heat, deflect radiation, and reduce thermal load. They take inspiration from spacecraft re-entry shielding, but adapted for continuous flight instead of a single atmospheric pass. Adaptive materials. Some new alloys can change their physical properties as temperatures rise, becoming more robust instead of weaker. This shape morphing and heat-adaptive behavior is a cutting-edge field shaped by nanotechnology and advanced computational modeling. It's not enough to survive high heat. You must also remain aerodynamic while doing it. Hypersonic flight completely changes the rules of aerodynamics. At Mach 1, you break the sound barrier. At Mach 5, the air itself becomes a different medium, dense, high energy, and prone to generating massive shock waves. Engineers are solving these challenges through wave rider designs. A wave rider uses its own shock wave to generate lift. Instead of fighting shock waves, it rides them, literally sliding through the air on top of them. This concept dramatically reduces drag and heat. Needle-like nose cones. Sharp leading edges normally melt, but ultra-high temperature materials now allow aerodynamic forms that reduce compression heat. Computational fluid dynamics at extreme speeds. CFD modeling has advanced more in the past decade than in the previous 50 years combined. Engineers can now simulate airflow behavior at hypersonic speeds, with accuracy approaching real-world testing. The result: for the first time, we can design aircraft that won't disintegrate long before reaching cruising altitude. People often overlook this part, but passenger comfort at hypersonic speeds is an engineering challenge as complex as propulsion. At Mach 5+, G-forces during acceleration and deceleration must be carefully managed. The key is gradual, controlled ascent profiles that increase speed over time, much like current rocket-powered test vehicles. Vibration control is another critical factor. Hypersonic turbulence behaves differently from subsonic turbulence, and engineers are exploring structural damping systems and cabin isolation designs that keep vibration away from passengers. Noise is also a formidable challenge. Hypersonic engines are loud by nature, but cabin insulation, active noise cancellation, and innovative structural designs can dramatically reduce sound exposure. Interior materials with high acoustic dampening properties are being integrated into conceptual cabin models. Cabin layout itself changes with hypersonic travel. Ultra-fast trips don't require lie-flat seats or long-haul amenities. Instead, the emphasis shifts toward ergonomic seating, panoramic digital displays, and continuous connectivity, because at these speeds, you won't be airborne long enough to sleep. Hypersonic cabins aren't about luxury, they're about resilience, stability, and lightweight efficiency. If hypersonic travel becomes a commercial reality, the global implications will be profound. Global companies could conduct in-person meetings within hours, not days. International branches become functionally local. Deal-making accelerates. Supply chains that rely on urgent transport, like semiconductors, medical materials, or critical components, would shrink from multi-day delivery windows to same-day arrival. Tourism long-haul travel currently deters many would-be explorers. With hypersonic flight, you could spend a weekend in a country that today requires an entire day just to reach. Global tourism would become more accessible, more spontaneous, and less punishing on the body. Humanitarian impact. Rapid response capabilities would be one of the most transformative outcomes. Disaster relief could be dispatched across the world within hours. Medical supplies, emergency responders, and critical equipment could reach anywhere faster than ever thought possible. The movement of people, goods, and ideas accelerates, and the world as we know it would reshape around those new possibilities. The future is promising, but it is not without obstacles. Regulation hypersonic aircraft create new categories of safety standards. Certification processes must be updated to account for unprecedented speeds, materials, and aerodynamic profiles. Infrastructure airports are designed for conventional jets. Hypersonic aircraft require different fueling systems, new runway materials, specialized maintenance facilities, and potentially even dedicated corridors of airspace to manage acceleration arcs and sonic boom footprints. Prototypes and demonstrators exist. Military hypersonic vehicles have successfully flown. Private aerospace companies are testing early concepts, but passenger-ready aircraft require a much higher threshold of safety and reliability. Realistically, experimental civilian hypersonic flights could emerge in the 2030s. Limited commercial service may follow in the 2040s, but the foundational technologies enabling Mach 5 plus passenger travel are being built now. Not imagined, not theorized, but engineered. Today we've explored the propulsion systems that rewrite the physics of flight, the materials that can withstand temperatures hotter than volcanic lava, the aerodynamic strategies that tame shockwaves, and the world that emerges when cities become minutes apart instead of oceans away. The dream of fast travel didn't die with Concorde, it paused, waiting for humanity to catch up technologically. And now, with advances in hypersonics, computational modeling and material science converging at the same moment, that dream is accelerating again. The fastest air travel humanity has ever engineered is no longer a distant fantasy. It's a frontier being actively shaped, with consequences that could redefine business, tourism, geopolitics, and personal mobility. The question isn't if we will fly at Mach 5, it's how soon you'll be able to buckle in for the ride. No more, be more.